So before spring break, we ended talking about Ampere's law. And now we want to do an example of that by finding the magnetic field in a wire. Now, you remember the magnetic field outside of a wire. So if you had a wire and you got current flowing through the wire, I, and you're some distance r away from that, you remember from before spring break, the magnetic field there is going to be equal to mu naught I over 2 pi r. Okay. So, but the question then would be, what if we had a wire like that, and we had current going down the wire, but rather than looking outside the wire, we look at a point in the wire in which r is less than big R, where big R is the radius of the wire. In that case, what would be the magnetic field? Is the magnetic field only outside the wire, or is the magnetic field also inside the wire? So that's what we want to figure out. Okay, so remember Ampere's law. So you've got you got some current here, and it makes a magnetic field. You go around this. In fact, anywhere you have a magnetic field, if you go through the magnetic field on a closed path, then the magnetic field is going to be going one way, it's going to go one way, go other way. So an integral around that enclosed path, B dot ds, would in principle all cancel out unless you had a source of magnetic field in there, and that would be a current. So this would be equal to mu naught times I. The I is the enclosed current. So that's the amount of current that goes through your Amperian loop that you draw. Okay, so with our wire here, let's zoom in on the wire. So we got current flowing down the wire. Okay, and so if you were to put your eye here and look down the wire, then you would see current going through the wire. Well, the current is going through the wire all over the place here. So it's not necessarily just going to the outside of the wire. It's going all through the wire. So it's spread out. Now, you remember when we first started talking about current, we defined current density. Current density is going to be current over area. So let's consider a case in which we are looking at a wire, and the wire has a current of 1.25 amps. And let's say that the radius is going to be 0.75 millimeters. And so I want to know what's the current density in there. So the current density is going to be 1.25 amps divided by 0.75 millimeters. Well, that's actually not really what we want, because we want this to be in SI units. So that would be not this. Actually, that's wrong in several ways. That should be area. So the area is pi r squared. So this is I over pi r squared. And so what you'd want is pi times 7.5 times 10 to the minus 4 meters squared. Okay, and so that's really what you want there. And so that's going to be equal to 7.07 times 10 to the fifth amps per square meter. So there is your current density. Okay, now how does that help us here? Well, imagine our wire. We got current flowing down the wire. You are looking at it from here. The radius of the wire, R, is 0.75 millimeters. But suppose you want to know at some distance, little r, of 0.25 millimeters from the center of the wire, what's the magnetic field at that spot right there? Okay. So the way I've drawn it, the magnetic field is going to be going around this way. It's going to be going around clockwise as you're looking at it, because right-hand rule, you point your thumb in the direction the current's going, your fingers curl around in that direction. Okay. So integral B dot ds, going around that little loop, is going to be equal to mu naught I. Now, this is enclosed I. So that's going to be J times the area. So that means it's going to be J times pi little r squared. So that little r is going to be the area of that little small circle right there. Okay. Integral B dot ds. Integral B dot ds, it's just going to be B integral ds. So that's going to equal the mu naught I. Well, that's going to be B times S. S is the distance around. So B times 2 pi r, that's the distance around the circle, and that's equal to mu naught times I. Well, I is equal to J times pi r squared. So the pi's cancel. That r cancels one of those r's right there. So the magnetic field is going to be mu naught J r divided by 2. So that's going to be equal to 4 pi times 10 to the minus 7 Tesla meter per amp, okay, times J, which is 7.07, times 10 to the 5th amps per square meter, okay, times R, 2.5 times 10 to the minus 4 meters. Remember, you need to have this in SI units, divided by 2. And so that gives us a magnetic field of 1.96 times 10 to the minus 10 Tesla. Or, if you'd like to write it a little bit neater, that's 0.196 nanotesla. Either one of those is okay. So there we have the magnetic field at that distance. Well, let's go back and look at this. We have that B equals mu naught JR divided by 2. Okay. So mu naught JR divided by 2. That means that if you were to look at this magnetic field, this distance of function of r goes linearly up until you reach the point of r equals r. At that point, it's going to start dropping with distance as 1 over r. So it's going to start dropping as 1 over r after that distance, because outside the magnetic field is going to be mu naught I over 2 pi r.